We're about to go into scikit-learn and do in 3 lines what took you hours and hours to do with gradient descent with loads of code. So why did we bother? Well, besides the fact that gradient descent is the one thing that underlies probably all of machine learning nowadays, it's probably the most important thing for you to know about. Besides that, it also gives you insight into various other techniques. We're just going to break out for a second, and I'm going to write a little bit on the slides to try and show you how, when you did gradient descent just now, you actually created your first ensemble of methods, and you also actually created your first gradient boosting machine. So let's try and understand that together. Ignoring the intercept for the moment, assuming that x is the lot area, our prediction is given by beta 1 times x. But if you remember how we created beta 1 using gradient descent, we initialized with a 0, and then we added a first step, and we added a second step, and we continued adding steps, as many as we needed until gradient descent converged. This means that we can actually write our prediction as follows. Prediction equals step 1 times x plus step 2 times x, and so on. You can therefore think of this simple linear model as a sum of lots of different models. Here's the first model, here's the second model. Later on we're going to come across the idea of ensembles, which is adding models together to get a better model. And in some ways that's exactly what this does. Let's just write this out in a slightly different way. If we call the step size eta, then the prediction is going to be equal to the step size multiplied by a function which is correlated with the errors, plus eta, which was another step, times another function which is correlated with the errors at this stage, times another function. You might remember that when we worked out the gradient, we noticed that these gradients were essentially functions that were correlated in some ways with the prediction errors at each stage of building the model. Now these functions over here are particularly simple functions. They were just some kind of sum of errors times lot area or something like that. We could though make these functions much more complicated. We could replace each function with a decision tree. We'll talk later on about exactly what decision trees are. If we did do that, and we worked out in each step a decision tree which was correlated with the errors, we would have discovered a very powerful form of gradient boosting, which is used in XGBoost, in CapBoost, and in various other things that we will encounter in a few weeks' time. I hope that made some kind of sense. It's not massively important at this stage, but I did want to demonstrate how understanding gradient descent can give you an insight into various advanced forms of machine learning.